That shimmering river of light in our night sky, a path our ancestors thought was made of divine milk, is an illusion. It is a city of 100 billion suns, a place of dying stars and cosmic beasts. Today, we journey into its violent, beautiful heart to uncover the true story of our home. If you could escape the silent, insistent pull of Earth and rise above the glittering tapestry of the stars, you would witness a spectacle of impossible scale. Below you, our galaxy, the Milky Way, would unfurl like a divine pinwheel, a glowing spiral of light adrift in the endless velvet dark. From this serene vantage point, it looks calm, eternal, a masterpiece of cosmic stillness. But this tranquility is a profound illusion. For within that silent, spinning city of stars, a drama of unimaginable violence and creation is playing out across eons. Stars are being born in incandescent fury and dying in cataclysmic explosions. Entire solar systems are whipping around a mysterious center at speeds that defy comprehension. Giant spectral clouds of gas and dust, the ghosts of old stars, and the seeds of new ones drift, collapse, and ignite. And at its very heart, shrouded in dust and mystery, lies a beast of such epic proportions. Its gravity holds 100 billion suns in its thrall. Only in the most recent flicker of cosmic time have we, its inhabitants, begun to truly understand what the Milky Way is. We have charted its luminous winding arms and discovered the faint, ghost-like galaxies that orbit it like loyal moons. Yet for all we have learned, the darkness holds more questions than answers. In this journey, we will follow these threads of light and shadow, piecing together one of the most epic stories in the universe. We will travel from the dawn of human wonder to the cutting edge of scientific discovery, from the chaotic furnace of the galactic core to the lonely silence of its outer halo. Prepare yourselves for a voyage into power beyond imagination. This is the story of our galactic home. Long before the word galaxy existed, long before science gave it a name, or humanity understood that stars were distant suns, there was a pale, shimmering river of light stretched across the deepest night sky. On clear, moonless nights, people everywhere could see it. It arched overhead like a great celestial path, a bridge between horizons. Some saw it as a plume of smoke from a divine fire. Others imagined it as a celestial river, its waters made of starlight. Many believed it was the trail left behind by gods or spirits on their journeys through the heavens. This was the Milky Way, our home, seen not as a structure of stars, but as a myth woven into the fabric of reality. In those ancient times, the cosmos was an intimate, living entity. There were no telescopes to measure the flicker of distant light, no spectrographs to decode the chemistry of the stars. All they had were their eyes, their stories, and their skies. The ancient Greeks, who were among the first to give written names to the constellations and chronicle their movements, saw the Milky Way as a direct product of divine drama. One of their most popular legends comes from the tale of the goddess Hera and the infant Heracles. As the story goes, Heracles, born of a mortal woman, but fathered by the king of the gods, Zeus, was brought to Hera to nurse while she slept a trick to grant him immortality. When Hera awoke and realized a strange child was at her breast, she pushed him away in shock. Her divine milk spilled across the heavens, creating the luminous arc we see today. The Greeks called it the Galaxias Kyklos, the Milky Circle. From this ancient myth, the very word galaxy was born. Far across the world in ancient China, astronomers kept meticulous records of the stars for centuries, mapping their slow dance with remarkable precision. They had their own name for the Milky Way, the Silver River, or Yin-He. To them, the band of light was a literal celestial waterway, vast and uncrossable. One of their most beloved and enduring stories tied to it is the legend of the Weaver Girl and the cowherd. According to this tale, the two lovers represented by the bright stars, Vega and Altair, were tragically separated by this silver river, allowed to meet only once a year on the 7th day of the 7th lunar month. On that day, a bridge of magpies would form across the celestial waters, allowing the lovers a brief reunion. This story is not just a relic of the past. It is still celebrated today in the Qixi festival, often called Chinese Valentine's Day. And in the summer sky, the stars Vega and Altair still shine brightly on opposite sides of the Milky Way, their silent, distant love story playing out for all to see. The story of the Milky Way was not just written by the Greeks and the Chinese. It was a global narrative told in countless languages under different skies. Further west, in what is now the Middle East, the ancient Mesopotamians saw the sky as a place deeply entwined with the fates of gods and mortals. In Babylonian culture, the heavens were a mirror of the earth, and the Milky Way was often thought to be the celestial reflection of their own great rivers, the Tigris or Euphrates, carried into the stars. In some myths, it was linked to the primordial sea dragon Tiamat, a goddess of chaos whose body was used to create the heavens and the earth after a great cosmic battle. The shimmering band of stars was a scar from that creation, a reminder of the universe's violent birth. Across the vast continent of Africa, traditions varied immensely by region, each culture weaving its own meaning into the stellar tapestry. Among the San people of southern Africa, the Milky Way was seen as the spine of night, a powerful structural element holding the sky together. Some of their stories described it as the embers of a great campfire thrown into the sky by an ancient girl, or as the celestial dust kicked up by a thundering herd of divine animals. It was a guide, a map, and a source of cosmic order. In parts of West Africa, it was also known as the backbone of night, a phrase so evocative it would one day title a modern documentary on astronomy, a testament to the enduring power of these ancient metaphors. In the cold climes of northern Europe, the Norse people had stories of their own. While their myths are better known for the dramatic tales of Thor Odin and the final battle of Ragnarok, the Milky Way was likely seen as Bifrost, the shimmering rainbow bridge that connected Midgard, the realm of humans, to Asgard, the home of the gods. It was the road traveled by deities and the souls of fallen warriors on their way to Valhalla. In this worldview, the sky was not a distant, abstract space, but an active theater of divine will, where every star and celestial feature played a role in the epic fate of gods and men alike. Among the indigenous peoples of the Americas, the interpretations were often profoundly poetic and rooted in the intricate rhythms of the natural world. The Inca of the Andes saw the Milky Way not just as a band of stars, but as a place filled with dark constellations, what we now call dark nebulae. These were not empty spaces, but celestial animals, a llama, a fox, a serpent, a toad. To the Inca, these dark shapes were as real and vital as the bright stars. They watched them shift through the seasons, using their appearance as a divine calendar for planting, harvesting, and ceremony. For the Lakota people of North America, the Milky Way was the Wanagi Thachanku, the spirit path, a road taken by souls after death on their journey to the afterlife. It was a path of transition, a sacred river separating the world of the living from the world of the spirits. Even in regions without written language, these ideas were kept alive for millennia through powerful oral traditions. The Aboriginal Australians, with some of the oldest continuing cultures on Earth, had remarkably detailed sky stories. The Yolngu people of Arnhem Land saw the Milky Way as a great canoe, the Larpen carrying ancestral beings across the sky. Its shimmering light was the reflection of their fires on the surface of the celestial waters. These stories were not just entertainment. They were maps, calendars, and moral lessons all wrapped in the stars. Without telescopes or physics, these ancient peoples knew that the Milky Way mattered. It was a source of awe, and from that awe, they built the very foundations of wonder, curiosity, and eventually the science that would one day reveal its true, unimaginable scale. For a very long time, for millennia, humanity believed that the Earth was still steady and at the absolute center of everything. The sky, they thought, moved around them in a perfect, predictable ballet. The sun rose and set a reliable celestial engine. The stars wheeled overhead in a grand, unified rotation. The moon, a loyal companion, traveled across the heavens in its appointed phases. To the human eye, this model was not just a theory, it was self-evident truth. After all, the ground beneath our feet feels firm and unmoving. The stars, the planets, and the sun appear to dance around us. It felt natural, right, and deeply profound to believe that Earth was the fixed heart of the universe. This idea was not mere folklore. It was codified and championed by the most influential thinkers of the ancient world. The Greek philosopher Aristotle, a titan of intellectual thought, argued that the heavens were perfect, eternal, and unchanging, made of a fifth element, the ether. In his cosmic model, a stationary Earth sat at the center of a series of nested crystalline spheres, each carrying a planet or star on its journey around us. This was a universe of divine order and geometric perfection. Later, the astronomer Claudius Ptolemy, working in the Great Library of Alexandria in the 2nd century AD, refined this geocentric system into a detailed mathematical model that would dominate Western thought for over 1,400 years. In Ptolemy's universe, the Earth sat still, while the planets, sun, moon, and stars spun around it in perfect circles. His system, however, was notoriously complicated. To account for the observed motions of the planets, especially their strange habit of wandering backward in the sky, a phenomenon called retrograde motion, Ptolemy had to introduce a complex system of circles moving within circles known as epicycles. But it worked. It seemed to match what people saw in the sky, and it provided a predictive framework that was, for its time, remarkably successful. For over 1,000 years, Ptolemy's model was taught as fact. It was not just an astronomical theory. It shaped the way people thought about the universe, their place within it, and even the nature of God. The Christian Church in Europe adopted this model wholeheartedly as it aligned perfectly with religious views that placed Earth and humanity at the center of divine creation. To question the structure of the heavens was not merely seen as foolish. It was a dangerous act of heresy, a challenge to the established order of both God and man. The universe was a closed, comforting, and human-centered place. Earth was the stage, and the heavens were a grand celestial clockwork built for our benefit. This belief, so deeply ingrained in philosophy, religion, and common sense, would hold sway for centuries, a beautiful and powerful illusion that placed humanity at the very heart of existence. For centuries, the geocentric universe of Ptolemy reigned supreme, a seemingly unassailable fortress of thought. But then quietly, almost imperceptibly, something began to shift. In the 1500s, a quiet but radical idea started to take form in the mind of a Polish mathematician and astronomer named Nicholas Copernicus. He began to wonder whether Ptolemy's model, with its fantastically complex system of epicycles, truly made sense. The motions of the planets, particularly their retrograde loops, were too messy, too forced under the old system. The circles within circles felt like a desperate patch on a flawed design, an inelegant solution to a persistent problem. What if Copernicus thought the problem wasn't with the planets, but with our perspective? What if the Earth was not the still center of creation? He proposed a revolutionary new model, one that was shockingly simple in its conception. What if the sun, not the Earth, was at the center of the universe? What if the Earth was just another planet spinning on its axis once a day and orbiting the sun once a year? This idea, the heliocentric model, made the backward movement of the planets almost trivial to understand. It was no longer a real motion, but an apparent one, like watching a slower car from a faster-moving train. It was a simple, elegant, and mathematically beautiful idea. But it was also deeply unsettling. To demote the Earth from its central throne was to demote humanity itself. Copernicus, a canon in the Catholic Church, hesitated to publish his work. He was acutely aware of how controversial, even heretical, it would be. He spent decades perfecting his masterwork, De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres, and only allowed it to be published shortly before his death in 1543. By that time, his health was failing, and he may have never known the full extent of the trouble and inspiration his idea would bring. At first, not much changed. Copernicus's book spread quietly, printed in Latin, and read mostly by other astronomers and mathematicians. Many still clung to the comforting certainty of the old geocentric system, but among the intellectual elite who read it, a crack had appeared in the foundations of the cosmos. The idea that Earth was not the center, that we were just one planet among others orbiting a star, was slowly, inexorably taking root. The old universe, a place of perfect spheres and divine order with humanity at its heart, was beginning to tremble. The revolution had begun not with a bang, but with a whisper. The seed of revolution planted by Copernicus might have remained dormant for decades, a curious footnote in academic circles had it not been for one man and one invention. The man was Galileo Galilei, and the invention would forever change our relationship with the heavens. Born in Pisa, Italy, in 1564, Galileo was a polymath with an insatiable curiosity about the world. He studied motion-built machines and relentlessly tested ideas that others had only debated in theory. But it was an invention from the early 1600s that would define his legacy, the telescope. The spyglass had just been invented, and it didn't take long for Galileo to hear of it build his own and dramatically improve upon its design. When he pointed his powerful new instrument toward the sky, he saw things no human had ever seen in such detail, things that directly contradicted the perfect, unchanging heavens of Aristotle and Ptolemy. He saw that the surface of the moon was not a smooth, perfect orb, but was scarred with mountains and craters just like the Earth. He saw sunspots, dark blemishes that marred the supposedly flawless face of the sun. Most damningly, he discovered that the planet Jupiter had moons of its own, 4 of them, that clearly orbited the giant planet, not the Earth. Here was a miniature solar system, a clear proof that not everything in the heavens revolved around our world. And perhaps his most crucial observation, he saw that the planet Venus went through a full set of phases, just like our moon. This was something that could only be explained if Venus was orbiting the sun, sometimes passing between the sun and Earth, and sometimes moving behind it. All of these discoveries pointed in one inescapable direction: Earth was not the center. The heavens were not perfect. The old models, for all their historical weight and philosophical beauty, could not explain what Galileo was now seeing through his lens. He published his explosive findings in 1610 in a short, accessible book called Sidereus Nuncius, the Starry Messenger. It caused an immediate uproar. The Catholic Church, still deeply tied to the Ptolemaic view, reacted with alarm. Galileo's ideas were seen not as scientific advancement, but as a direct threat to religious authority and the divine order of the universe. In 1616, Copernicus's heliocentric theory was officially declared heretical. Galileo was formally warned not to teach or support it, but Galileo, convinced by the evidence of his own eyes, did not stop. He continued to write, and in 1632, he published his masterpiece, dialogue concerning the two chief world systems. Though cleverly written as a conversation between three characters, one supporting Copernicus, one supporting Ptolemy, and one neutral observer, the book was a clear and powerful argument for the sun-centered model. The response from the Church was swift and severe. Galileo was summoned to Rome to stand trial before the Inquisition. Under threat of torture, the aging astronomer was forced to recant his views. He spent the rest of his life under house arrest, a prisoner of his own genius. But the damage to the old universe was done. The telescope had revealed too much. The stars were no longer just distant lights on a black dome. They were worlds, and the cosmos was infinitely larger and more complex than anyone had ever dreamed. While Galileo was waging a dramatic and public battle for the heliocentric model, another brilliant mind was quietly uncovering the deeper mathematical rules that governed the cosmos. Johannes Kepler, a German astronomer and mathematician, was obsessed with finding the divine harmony he believed must underlie the structure of the universe. He initially thought the planets' orbits were set by a series of nested geometric solids, a beautiful but ultimately incorrect idea. His true breakthrough came from a place of painstaking, almost maddeningly difficult work, analyzing the meticulously collected observational data of the planet Mars. Working with the data of his predecessor, the great astronomer Tycho Brahe Kepler tried to fit the orbit of Mars to a perfect circle, as Copernicus had assumed. But it never quite worked. There was always a small but persistent discrepancy. For years he wrestled with this problem, refusing to ignore the tiny error. This stubborn refusal to accept an imperfect fit led him to a revolutionary discovery. Planets did not move in perfect circles. They moved in ellipses, a slightly flattened circle with the Sun not at the center, but at one of the two foci. This was Kepler's first law, and it shattered a 2,000-year-old belief in the perfection of celestial circles. As he continued to analyze the data, he discovered a second principle. Planets do not move at a constant speed. They move faster when they are closer to the Sun in their elliptical orbit, and slower when they are farther away. This meant that an imaginary line connecting a planet to the Sun would sweep out equal areas in equal intervals of time. This was Kepler's second law, a rule that described the changing rhythm of the planetary dance. Finally, after years more of calculation, he uncovered a third, even more profound relationship, a harmonic law that connected the orbits of all the planets to each other. He found that the square of a planet's orbital period, the time it takes to go around the Sun, is directly proportional to the cube of its average distance from the Sun. This meant that the farther a planet was, the longer and slower its orbit would be, but in a precise, predictable mathematical way. Together, Kepler's three laws of planetary motion provided an incredibly accurate and powerful framework for the heliocentric model. They explained the observed movements of the planets with far greater precision than any system before them. The old clunky machinery of epicycles was no longer needed. In its place was a universe of elegant elliptical paths governed by a hidden mathematical harmony. Kepler had found the rules of the celestial dance, but he didn't yet know the why. He suspected some kind of force emanated from the Sun, a magnetic or spiritual influence that pushed the planets along their paths. The final piece of the puzzle, the explanation for what this force was, would have to wait for the next great mind to take the stage. The stage was set. Copernicus had moved the Earth. Galileo had seen new worlds. Kepler had described their elegant elliptical dance. But the great unanswered question remained. Why? Why did planets move in ellipses? What invisible force held them in their orbits and prevented them from flying off into the void? The answer would come from one of the most brilliant minds in human history, Sir Isaac Newton. In the late 1600s, living in an England roiled by plague and political turmoil, Newton formulated a set of laws that would not only explain the heavens, but redefine our understanding of the physical world. His great insight was one of stunning universality. He proposed that the force that caused an apple to fall from a tree to the ground was the very same force that held the moon in orbit around the Earth, and the Earth in orbit around the sun. This force, which he called gravity, was not a terrestrial phenomenon or a celestial one. It was universal. It was a ghostly, invisible hand that reached across the vastness of space, pulling all objects with mass toward one another. Newton described this force with a simple yet profoundly powerful mathematical equation. The force of gravity between two objects, he stated, is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This meant that the more massive the objects, the stronger the pull, and the farther apart they were, the weaker the pull became, diminishing with distance in a precise, predictable way. With this law of universal gravitation combined with his three laws of motion, Newton could explain everything from the path of a cannonball to the orbit of a comet. The solar system was no longer a place of divine will or mysterious harmonies. It was a grand, intricate machine that followed knowable mathematical rules. The elliptical orbits Kepler had discovered were a natural consequence of this inverse square law of gravity. Newton's work, published in his monumental Principia Mathematica in 1687, was the final triumphant capstone of the scientific revolution. The geocentric universe was not just disproven, it was replaced by a vast clockwork cosmos governed by a single universal force. But this new understanding, while solving one mystery, opened the door to another, even larger one. If the Earth was not the center, and the Sun was just one star among countless others, then what were all those other stars in the sky? What was the shape and scale of this grand system we were a part of? The universe began to stretch its boundaries, expanding in the human mind. The Earth moved around the Sun. The Sun was just one of many stars. And those stars, it was slowly becoming clear, might be part of a larger system too, a vast spinning island of light we would one day call the Milky Way galaxy. With the solar system's mechanics now understood, the minds of astronomers turned to the grander structure in which it sat, the Milky Way itself. In the late 1700s, one astronomer, William Herschel, along with his sister and collaborator Caroline Herschel, embarked on one of the most ambitious projects of their time to map the shape of this stellar system. Armed with powerful new telescopes of his own design, Herschel began a painstaking process of what he called stargazing. His method was simple in concept, but monumental in execution. He would point his telescope to a specific patch of sky and meticulously count every star he could see within its field of view. He repeated this process for hundreds of different regions, slowly building a census of the heavens. His underlying assumption was that the stars were on average spread out evenly through space. Therefore, if he saw more stars in one direction, it meant that the galaxy extended farther that way. If he saw fewer, it meant he was looking toward a closer edge. After years of this laborious work, Herschel constructed the first ever map of the Milky Way based on observational data. His map depicted a flattened, irregular disc-like structure, almost like a grindstone. Critically, it placed our Sun very near the center. From our vantage point, it seemed we were at the heart of this great collection of stars. It was a remarkable first attempt, a heroic effort to grasp the scale of the cosmos. However, Herschel's map was fundamentally flawed, though he had no way of knowing it at the time. He could not account for a crucial invisible component of the galaxy: interstellar dust. We now know that vast clouds of gas and dust drift between the stars, and these clouds act like a thick cosmic fog, blocking the light from more distant objects. Because of this dust, Herschel was only seeing our local stellar neighborhood. The dimming effect of the dust made it seem like the galaxy ended just a few thousand light-years away in every direction, creating the illusion that we were at the center of a relatively small star system. Despite its inaccuracies, Herschel's work was a revolutionary step. He was the first to treat the Milky Way not as a mere band of light, but as a physical, measurable structure. He and Caroline also discovered thousands of new objects, including faint, cloudy patches they called nebulae. Some of these they correctly reasoned were unresolved clusters of stars. Others, however, would later be revealed to be something far more profound, entire island universes, other galaxies lying far beyond our own. The true shape of our galaxy remained hidden, but the quest to unveil it had begun. The answer would not be found in visible light alone. It lay waiting in the invisible parts of the spectrum, in forms of light our eyes were never meant to see. For over a century after Herschel, our view of the Milky Way remained shrouded in mystery, our vision blocked by the impenetrable curtains of interstellar dust. Astronomers knew there was more to the galaxy than they could see, but they had no way to peer through the cosmic fog. The breakthrough came not from building bigger optical telescopes, but from learning to see the universe in entirely new forms of light. Light, it was discovered, is more than the rainbow of colors our eyes can detect. It is a vast spectrum of electromagnetic radiation. There are wavelengths shorter and more energetic than visible light, like ultraviolet and X-rays, and there are wavelengths that are longer and less energetic, like infrared and radio waves. It was these longer wavelengths that held the key. They possess a special, almost magical ability. They can pass straight through the dense clouds of dust that absorb and scatter visible light. Infrared light, which we feel as heat, is emitted by objects that are not hot enough to glow visibly, such as cool stars forming protostars and the warm dust clouds themselves. By detecting this faint heat glow, astronomers could begin to trace the structures hidden deep within the galaxy's dusty heart. But the true revolution came with radio waves. These are the longest wavelengths of all, and they can travel through even the thickest clouds of gas and dust, almost completely undisturbed. In the mid-20th century, a new kind of astronomy was born: radio astronomy. It didn't use glass lenses or polished mirrors. Instead, it used giant dish-shaped metal antennas to collect the faint radio signals raining down from space. These invisible signals, carrying information from the most obscured corners of the cosmos, would finally allow us to pull back the veil and see the Milky Way's true form for the first time. The silent, static-filled sky was about to speak, and its message would reshape our understanding of our galactic home. One of the first and most profound discoveries of the new radio astronomy came from listening for the faintest of cosmic whispers, the song of the hydrogen atom. Hydrogen is by far the most abundant element in the universe, the raw fuel from which stars and galaxies are made. In the vast cold emptiness of interstellar space, most of the gas is made of neutral hydrogen atoms. In the 1940s, physicists predicted that these hydrogen atoms should emit a faint but specific radio signal. An atom of hydrogen consists of a proton and an electron. Both of these particles have a property called spin. On rare occasions, the electron can spontaneously flip its spin relative to the proton. When this tiny quantum leap occurs, the atom releases a minuscule puff of energy in the form of a radio wave with a very specific wavelength, 21.1 centimeters. This 21-centimeter line, though incredibly faint and emitted by any single atom only once every few million years, comes from countless trillions of atoms spread across the galaxy. In the 1950s, radio astronomers began to point their new telescopes toward the galactic plane, tuning them to listen for this precise frequency. What they heard transformed our map of the galaxy. As they scanned the sky, they found that the hydrogen wasn't spread out evenly. Instead, it was concentrated in long, curved, flowing structures, immense rivers of gas that wrapped around the center of the galaxy. These were the spiral arms. For the first time, we had direct, unambiguous evidence that the Milky Way was a spiral galaxy. Instead of being a simple, flattened disk of stars as Herschel had imagined it, possessed a grand, elegant structure. The arms curled outward from a dense central region tracing a pattern of cosmic creation. By using another clever trick, the Doppler effect astronomers could even map these arms in 3 dimensions. Just as the pitch of a siren changes as it moves toward or away from you, the wavelength of the 21 cm line shifts depending on the motion of the gas cloud emitting it. By measuring these subtle shifts, scientists could determine how fast different parts of the galaxy were rotating, revealing the grand swirling motion of the spiral arms. The silent hydrogen gas, scattered across tens of thousands of light-years, had given us the first true blueprint of our home. While radio waves unveiled the grand spiral structure of the galaxy's arms, the very heart of the Milky Way remained a deep mystery, impenetrably shrouded by dust. The next great leap in understanding came from infrared telescopes, which could pierce this dusty veil and see the heat glow of the stars within. In the 1980s and 1990s, NASA launched missions like the infrared astronomical satellite IRIS, and later the more powerful Spitzer Space Telescope. Orbiting high above Earth's atmosphere, which blocks much of the infrared light from space, these observatories gave us our first clear view into the galactic core. What they found was not a simple spherical bulge of stars. Instead, the data revealed a crowded complex and elongated region. At the heart of it all was a massive bar-shaped structure of stars, a cosmic backbone stretching for thousands of light-years through the galaxy's center. This discovery fundamentally changed our classification of the Milky Way. Our galaxy was not just a simple spiral, it was a barred spiral, a common but more complex form seen in many other galaxies across the universe. This central bar is thought to form from the gravitational instabilities in a rotating stellar disk. Over billions of years, the orbits of stars in the inner galaxy can become elongated and aligned, creating a dense rotating bar. This structure is not just a passive feature, it's a dynamic engine. The bar's powerful gravity acts like a cosmic funnel, channeling gas from the inner spiral arms toward the galactic center. This inflow of gas can trigger furious bursts of star formation in the core and ultimately feed the supermassive black hole lurking at its heart. Infrared and radio maps were combined, creating a multi-wavelength portrait of the Milky Way. A picture emerged of a majestic, spinning city of stars, a thin disk with at least 4 major curving spiral arms, a thick, elongated, bar-shaped bulge at its center, and all of it enveloped in a vast spherical halo of ancient stars and mysterious dark matter. Still mapping our galaxy remains a uniquely difficult challenge. Unlike the distant galaxies we can photograph from the outside, we can never step back and take a picture of our own. Every map of the Milky Way is a painstaking reconstruction, an intricate mosaic pieced together from countless signals arriving from every direction. It is a portrait painted from the inside out, a story told in invisible light. Knowing the overall shape of the galaxy raised another fundamental question: where precisely are we within this vast stellar city? For centuries, based on Herschel's flawed star counts, humanity had assumed a privileged position at the center. But the more we learned, the more we were displaced. The key to finding our true address lay in measuring cosmic distances with unprecedented accuracy. The breakthrough came from a special class of stars known as Cepheid variables. These are pulsating stars that rhythmically grow brighter and dimmer, and in the early 20th century, astronomer Henrietta Leavitt discovered a remarkable property. The period of a Cepheids pulsation is directly related to its true intrinsic brightness. This meant that by simply timing a Cepheids pulse, astronomers could know how bright it truly was. By comparing this true brightness to how bright it appeared from Earth, they could calculate its distance using a simple inverse square law. Cepheids became the universe's standard candles, reliable mile markers for mapping the cosmos. In the 1920s, astronomer Harlow Shapley used Cepheid variables within globular clusters, ancient spherical swarms of stars orbiting the galaxy, to map their distribution. He found that these clusters were not centered on the Sun, but on a point thousands of light years away in the direction of the constellation Sagittarius. This was the true center of the Milky Way. Our Sun was not at the heart of the galaxy. We were far out in the suburbs. Subsequent studies have refined this measurement. We now know that the solar system sits about 26,000 light-years from the galactic center. This places us roughly halfway out from the core to the visible edge of the galactic disk, which stretches about 100,000 light-years across. But knowing our distance was only part of the address. What about our neighborhood? The Milky Way's disk is not a uniform sea of stars. It's structured into grand spiral arms. Our solar system does not reside within one of these main bustling arms. Instead, we are located in a smaller partial arm, or spur, a kind of stellar side street that connects two of the larger arms. This structure is known as the Orion Arm, or sometimes the Orion Cygnus Spur. It is a relatively quiet branch, nestled between the denser, more active Sagittarius Arm, closer to the galactic center, and the Perseus Arm farther out. Our location might be cosmically fortunate. The main spiral arms are sites of intense star formation, frequent supernova explosions, and higher levels of dangerous radiation. Our quieter neighborhood may have provided the long-term stability necessary for life to evolve on Earth, sheltered from the most violent galactic weather. We live on a small planet orbiting an average star in a minor arm of a vast barred spiral galaxy, a humble address in a cosmos of unimaginable scale. The Milky Way is not a static object. It is a dynamic rotating system, a great cosmic carousel of stars, gas, and dust. Everything within it, including our Sun and its entire family of planets, is in constant motion orbiting the galactic center on a journey of immense scale and duration. Our solar system is hurtling through space at a staggering speed of about 828,000 kilometers per hour, or roughly 514,000 miles per hour. At this velocity, it takes our Sun approximately 230 million years to complete one full orbit around the heart of the Milky Way. This vast span of time is known as a galactic year, or a cosmic year. To put this in perspective, the last time our solar system was in its current position in the galaxy, the first dinosaurs were just beginning to walk the Earth. The continents were merged into the supercontinent of Pangaea. Since the Sun was born some 4.6 billion years ago, it has completed this grand circuit only about 20 times. This constant sweeping motion is so smooth and immense that we cannot feel it. We are carried along oblivious on a celestial ride of epic proportions. The path of our orbit is not a perfect circle. It is a slightly elliptical journey that also involves a gentle bobbing motion. Like a horse on a carousel, our solar system oscillates up and down, passing through the dense central plane of the galactic disk, and then rising above it before falling back through again. This vertical cycle takes roughly 60 million years to complete. Some scientists have speculated that these passages through the galactic plane, where stars and gas clouds are more concentrated, could have consequences for Earth. The increased gravitational disturbances might stir up the Oort cloud, the distant reservoir of comets surrounding our solar system, potentially sending a shower of them toward the inner planets and triggering periods of increased impact events and mass extinctions. While this theory remains debated, it highlights the profound connection between our planet's history and our journey through the galaxy. We are not isolated. We are part of a larger, ever-changing cosmic environment. In the 1970s, a discovery was made that would fundamentally alter our understanding of the universe and reveal that the galaxy we see is only a tiny fraction of what is actually there. The astronomer Vera Rubin, along with her colleague Kent Ford, was studying the rotation of spiral galaxies, including our neighbor Andromeda. Using powerful spectrographs, they measured the speeds of stars at various distances from the galactic center. According to Newton's laws of gravity, which had perfectly described the motions of our solar system, the stars farther out from the center, where most of the visible mass like stars and gas is concentrated, should be moving much more slowly. Just as Neptune plods along in its distant orbit compared to the swift Mercury, the outer stars of a galaxy should be traveling at a leisurely pace. But that is not what Vera Rubin found. To her astonishment, the stars at the very edges of the galaxies were moving just as fast as the stars closer in. Their speeds were not dropping off as expected. They remained stubbornly, inexplicably high. The galaxies were spinning too fast. The visible matter, all the stars, gas, and dust they could account for, did not provide nearly enough gravitational pull to hold these fast-moving outer stars in their orbits. The galaxies should be flying apart. The only way they could be held together was if there was a vast amount of unseen, invisible mass exerting a powerful gravitational grip. This mysterious, non-luminous substance was given a name: dark matter. It was not a new idea. The astronomer Fritz Zwicky had proposed something similar for galaxy clusters decades earlier, but Rubin's work provided the most direct and compelling evidence to date. Her rotation curves, graphs, plotting orbital speed against distance, became iconic proof that galaxies were far more massive than they appeared. This was not a small discrepancy. The data suggested that for every gram of visible matter, there might be 5 to 10 grams of dark matter. The universe we could see was merely the luminous tip of a colossal cosmic iceberg. The discovery of dark matter forced a complete rethinking of the structure of our galaxy. The bright disk of the Milky Way, with its spiral arms and central bulge, was not the whole story. It was merely the visible component embedded within a much larger, more massive and completely invisible structure, the dark matter halo. This halo is thought to be a vast, roughly spherical cloud of dark matter that extends far beyond the visible edge of the galaxy, possibly for hundreds of thousands of light years, in every direction. It doesn't shine, it doesn't reflect light, and it doesn't interact with ordinary matter except through the relentless pull of gravity. It is the invisible scaffolding, the cosmic skeleton, upon which our galaxy is built. Without this halo, the Milky Way as we know it could not exist. Its rapid rotation would have flung its stars into intergalactic space long ago. The dark matter provides the extra gravitational glue needed to hold everything together, from the outermost stars to the satellite galaxies that orbit us. What is this mysterious substance? We still don't know. It is not made of protons, neutrons, or electrons, the stuff of ordinary matter. It is not dark clouds of dust or faint dead stars. Those would have been detected. The leading hypothesis is that dark matter is composed of a new type of subatomic particle, one that has yet to be discovered in our particle accelerators on Earth. These particles, often called WIMPs. Weakly interacting. Massive particles would be all around us, passing through our bodies and the Earth itself, as if we were ghosts, their presence felt only through their collective gravitational influence on the grandest scales. The halo is not perfectly smooth. According to cosmological simulations, it should be lumpy, filled with smaller, denser clumps of dark matter called subhalos. These are the remnants of the smaller dark matter structures that merged over billions of years to form the Milky Way's halo. Most of these subhalos are thought to be entirely dark, containing no stars at all. But some of the larger ones would have captured enough gas in the early universe to ignite star formation, becoming the dwarf satellite galaxies we see orbiting the Milky Way today. In a very real sense, the dark matter halo is the true galaxy, and the luminous disk we call home is just the radiant decoration settled at its center. Its immense, unseen mass dictates the motion of our solar system, the fate of our galactic neighbors, and the ultimate destiny of the Milky Way itself. If you could view the Milky Way from the side, you might picture a perfectly flat, thin disk, like a cosmic pancake. For many years, that was the standard textbook image. But as our tools for mapping the galaxy in 3 dimensions have grown more powerful, a more complex and dynamic picture has emerged. The Milky Way is not flat. It is warped, flared, and rippled its shape, telling a deep story of a life filled with gravitational turmoil and ancient encounters. The most dramatic of these features is a large-scale warp in the galactic disk. Like a vinyl record left in the sun too long, the outer parts of the Milky Way are bent. One side of the disk curves gently upward, while the opposite side dips downward. This gentle S-shaped curve affects the positions and motions of billions of stars and vast clouds of hydrogen gas, especially in the galaxy's outer reaches. What could cause an entire galaxy to bend like this? The most likely culprit is gravitational interaction. Our galaxy has not lived a solitary life. It is surrounded by smaller satellite galaxies, most notably the large and small Magellanic Clouds. As these companions orbit the Milky Way, their gravity tugs on the outer, more tenuous parts of our disk. Over millions of years, this persistent pulling and twisting can induce a wobble, a galactic warp that propagates through the stellar disk. The Magellanic Clouds, especially the more massive Large Magellanic Cloud, are considered the prime suspects for creating the warp we see today. As we move even farther out from the center, the disk doesn't just warp, it also flares. This means the disk gets progressively thicker with increasing distance from the center. The stars and gas clouds at the very edge are not confined to a neat, thin plane. Instead, they are spread out vertically, forming a puffier, more diffuse structure. This flaring is likely another scar from past interactions. The gravitational energy from passing galaxies can heat up the orbits of stars in the outer disk, kicking them into higher, more inclined paths and causing the disk to puff up. The outer regions of the galaxy are more fragile, more easily disturbed, and the flared edges are the visible evidence of this ongoing cosmic weather. The warped and flaring disk is not the only evidence of the Milky Way's tumultuous past. Data from space observatories, particularly the European Space Agency's Gaia mission, has revealed subtler but equally profound structures, ripples and oscillations moving through the stars themselves. The disk is not just bent. It is ringing like a bell that was struck long ago. Gaia, by measuring the precise positions and motions of over 1 billion stars, has allowed astronomers to create a dynamic 4D map of our galaxy. This map shows that stars don't just orbit smoothly around the center. Many of them are also moving up and down in a coordinated wave-like pattern. These vertical ripples are not random. They seem to emanate from a specific point and propagate outward through the disk. These are the echoes of a past collision. When a smaller dwarf galaxy plunges through the Milky Way's disk, It doesn't just pass through silently. Its gravity creates a powerful disturbance, a shock wave that travels through the disk like the ripple from a stone dropped in a pond. This gravitational wake perturbs the orbits of stars, lifting them up and pulling them down, creating the oscillating patterns that Gaia can now detect millions or even billions of years later. By tracing these ripples back to their origin, astronomers can reconstruct the history of these ancient impacts. One of the most significant events responsible for these ripples is thought to be the passage of the Sagittarius dwarf spheroidal galaxy, a small galaxy that is currently in the process of being torn apart and absorbed by the Milky Way. Models show that Sagittarius has punched through our galaxy's disk several times in its long, spiraling death dance. Each passage would have sent powerful gravitational waves rippling through our stellar neighborhood, leaving the signatures we see today. These features, the warp, the flare, the vertical ripples, paint a picture of a galaxy that is not a quiet, isolated island, but a living, breathing entity. Its shape is not static or frozen in time. It is constantly changing, sculpted by the gravitational forces of its companions, and forever marked by the scars of its violent history. When we look at the shape of the Milky Way, we are seeing the memory of ancient galactic battles written in the very positions and motions of the stars. At the heart of the Milky Way lies the central bulge, a dense, ancient concentration of stars. For a long time, it was imagined as a simple spherical cluster. But as infrared telescopes pierced the intervening dust, they revealed a far stranger and more complex structure. When viewed from the side, the Milky Way's bulge is not round. It is distinctly boxy or even peanut-shaped. This peculiar form is a direct consequence of the massive stellar bar that dominates the galactic center. The stars within this bar do not follow simple circular orbits. Instead, their paths are highly elongated and complex, tracing intricate patterns that, when combined, build up this three-dimensional structure. Many of the stars in the bulge are trapped in these bar-driven orbits, which swing them back and forth along its length. But their orbits also have a significant vertical component. They are lifted high above and below the main plane of the galaxy, creating the characteristic puffy or box-like appearance. This vertical structure is thought to be the result of a process called bar buckling. In computer simulations of galaxy formation, a newly formed stellar bar is initially flat, confined to the disk. But as it grows more massive and its rotation becomes more organized, it can become gravitationally unstable. Like a spinning ruler that starts to wobble, the bar can buckle in the middle, bending and puffing up vertically. This instability kicks stars into higher, more inclined orbits, transforming a flat bar into a three-dimensional boxy or peanut-shaped bulge. The stars that make up this bulge are mostly old red and metal-rich, some of them over 10 billion years old. This tells us that the bar and bulge formed early in the galaxy's history, likely growing organically from the material in the inner disk, rather than from a chaotic merger of other galaxies. This X-shaped or boxy structure is not just a curiosity. It's a key piece of evidence for how our galaxy evolved from the inside out, a story of slow dynamic change rather than purely violent collisions. It is a structure built not by external forces, but by the relentless, intricate dance of gravity within our own galactic heart. When astronomers map the density of stars in the central bulge, an even more surprising feature emerges from within the boxy peanut-like shape. If you tilt your view just right, especially when looking from a position slightly above or below the galactic plane, the bulge appears to have a distinct cross-like structure at its core. 4 arms of starlight seem to stretch outward from the center, forming a giant, glowing letter X. This stellar X is not an illusion. It is a real density enhancement, a place where the orbits of millions of stars happen to line up. It is the most visible signature of the complex orbital dynamics at play in the galaxy's barred heart. The X shape arises from the same family of banana-shaped and pretzel-shaped orbits that create the overall boxy bulge. Some of these highly inclined orbits have turning points that consistently place stars in the four lobes of the X, making these regions appear brighter and more densely populated than the areas around them. The discovery of this X-shaped structure was a triumph for both observation and theory. For years, computer simulations predicting the evolution of barred galaxies had shown that these X-shaped bulges should form naturally through the bar-buckling instability. When astronomers using data from infrared surveys like VISTA finally confirmed its existence in our own galaxy, it was a powerful validation of these models. It showed that our understanding of how galactic bars and bulges grow is on the right track. This structure, hidden from our eyes by thousands of light-years of dust, tells a story of gentle internal evolution. Unlike some galaxies whose central bulges are chaotic remnants of ancient smash-ups with other galaxies, the Milky Way's X-shaped bulge seems to have grown peacefully from the disk itself, sculpted by the slow, steady hand of gravity over billions of years. Right at the center of this stellar X sits our supermassive black hole, Sagittarius A. The bar and bulge act as a gravitational funnel steering gas and stars inward, providing the fuel that can occasionally awaken this sleeping giant. The X is more than just a peculiar shape. It is a fundamental component of the engine that drives the evolution of our galaxy's core. The most iconic features of the Milky Way are its majestic spiral arms, great sweeping arcs of light, gas, and dust that wind their way out from the central bar. These arms are not solid, permanent structures, like the spokes on a wheel. If they were, they would wind themselves up into a tight spiral and disappear within a few rotations of the galaxy. Instead, they are something far more subtle and fascinating. They are density waves. Imagine a traffic jam on a highway. The jam itself moves slowly down the road, but individual cars are constantly entering it, slowing down, and then exiting the other side to speed up again. The spiral arms of a galaxy work in a similar way. They are regions of higher density and gravitational compression that move through the galactic disk more slowly than the stars and gas clouds themselves. As stars and vast clouds of interstellar gas orbit the galaxy, they pass into these slow-moving density waves. Inside the arm, they are squeezed by the increased gravity. After passing through, they emerge on the other side and continue on their journey. The arms are persistent patterns, cosmic traffic jams, where the stuff of the galaxy temporarily bunches up. This compression has a profound consequence. When giant molecular clouds, cold, dense nurseries of future stars enter a spiral arm, the squeeze from the density wave can be enough to trigger their collapse. Gravity takes over the cloud's fragment, and countless new stars ignite. This is why the spiral arms shine so brightly. They are the primary sites of star formation in the galaxy, decorated with the brilliant, hot blue light of newborn stars. These massive young stars live fast and die young. They blaze with incredible intensity for a few million years before exploding as supernovae. Their short lives mean they don't have time to travel far from where they were born. As a result, they act like brilliant celestial markers tracing the path of the spiral arms like strings of holiday lights. Their intense ultraviolet radiation and powerful stellar winds also energize the surrounding gas, causing it to glow in the vibrant pinks and reds of emission nebulae, further highlighting these grand threads of creation. The spiral arms of the Milky Way are not uniform rivers of light. They are punctuated by colossal clouds of gas and dust where stars are born in spectacular fashion. These are the great stellar nurseries, the birthing grounds of new suns and solar systems. We now believe the Milky Way has 4 major spiral arms, though some are more defined than others. From the inside out, they are the Norma arm, the Scutum Centaurus arm, the Sagittarius arm, and the Perseus arm. Our own solar system drifts within a smaller branch between 2 of these, the Orion spur. Within these arms lie some of the most dramatic landscapes in our galaxy. In the Sagittarius arm, we find the W51 complex, one of the most massive and active star-forming regions in the entire Milky Way. It is a chaotic cauldron of collapsing gas, brilliant young star clusters, and expanding supernova remnants. Also in this arm lies the stunning Trifid Nebula and the vast Lagoon Nebula, a stellar nursery so large it is visible to the naked eye as a faint patch of light. Traveling outward, we encounter the Carina Sagittarius arm, which contains the spectacular Carina Nebula. This region is home to some of the most massive and unstable stars known, including the volatile superstar Eta Carinae, a ticking time bomb destined to explode as a hypernova. The nebula is a maelstrom of creation and destruction, carved and illuminated by the ferocious radiation of its stellar titans. In our own local neighborhood, the Orion Spur, we find the famous Orion Nebula, the closest massive star-forming region to Earth. At a distance of just 1/300 light-years, it offers us an unparalleled up-close view of the star birth process. Through telescopes, we can see newborn stars still swaddled in their dusty protoplanetary disks, the raw material from which future planets will form. The spiral arms are a battleground between gravity and pressure, darkness, and light. They are where the cycle of cosmic matter plays out on the grandest scale, where the cold, dark gas of the interstellar medium is forged into the fiery hearts of new stars, seeding the galaxy with the potential for new worlds and perhaps new life. As our journey takes us inward toward the brilliant, chaotic heart of the galaxy, the environment becomes increasingly extreme. Here, just a few dozen light-years from the central supermassive black hole, we find stellar clusters unlike anything in our quiet solar neighborhood. These are some of the densest, most massive, and youngest star clusters known in the Milky Way. 2 of the most famous are the Arches cluster and the Quintuplet cluster. The Arches cluster is a breathtakingly dense swarm of massive young stars. It is packed with over 100 brilliant hot blue stars, many of them more than 100 times the mass of our Sun, all squeezed into a region just a few light-years across. In comparison, the nearest star to our Sun is over 4 light-years away. Here, stars are practically on top of each other. These stellar behemoths produce ferocious stellar winds and pour out torrents of ultraviolet radiation, sculpting the surrounding gas into glowing arched filaments that give the cluster its name. Life in the Arches cluster is fast and violent. In just a few million years, many of its most massive stars will have already exhausted their fuel and exploded as powerful supernovae, blasting their surroundings with energy and seeding the galactic center with heavy elements. Nearby lies another remarkable group, the Quintuplet cluster. It is slightly older than the Arches, and its stars are beginning to show signs of aging. Some have already swelled into red supergiants, shedding their outer layers in thick shells of dust. The cluster gets its name from 5 unusually bright, dusty stars that were first spotted glowing in infrared light. These clusters orbit the galactic center, weaving through dense gas clouds and past the gravitational influence of Sagittarius A. The conditions here are so extreme that they challenge our theories of star formation. How can such massive stars form and survive in a region with such powerful tidal forces and intense radiation? Some scientists think they may have formed from the cataclysmic collapse of a single colossal gas cloud. Others suggest they may have formed farther out in the galaxy and slowly spiraled inward, captured by the immense gravity of the core. These clusters are cosmic laboratories, allowing us to study how stars form and evolve in the most hostile environments imaginable, offering a glimpse into the fiery heart of our galactic home. At the very gravitational center of the Milky Way, in the heart of the central star cluster, lies the most direct evidence for the existence of our galaxy's supermassive black hole. Here, astronomers have tracked the motion of a small group of stars, known as the S stars, as they perform a frantic high-speed dance around a completely invisible point. By using powerful telescopes equipped with adaptive optics to correct for the blurring effect of Earth's atmosphere, scientists have been able to follow the paths of these individual stars for decades. Their orbits are tight, fast, and highly elliptical. One star in particular, named S2, has become a cosmic celebrity. It completes a full looping orbit around the galactic center in just 16 years. During its closest approach, or pericenter, it comes within a mere 17 light hours of the central object, a distance only about 4 times that of Neptune from our Sun. At this point in its orbit, S2 is traveling at an astonishing speed of over 25 million kilometers per hour, nearly 3% the speed of light. No ordinary object could command such motion. The only explanation that fits the orbital data is a single compact object with an immense gravitational pull packed into an incredibly small space. By applying Kepler's laws to the orbits of S2 and its companions, astronomers have calculated the mass of this central object with remarkable precision. It must contain the equivalent of 4.3 million times the mass of our Sun. Yet this massive object gives off no light of its own. This is the smoking gun, the undeniable proof of the supermassive black hole we call Sagittarius A. The high-precision tracking of these stars has also provided a unique laboratory for testing Einstein's theory of general relativity in an extreme gravitational field. As S2 swooped past the black hole during its close approach in 2018, astronomers observed 2 key relativistic effects. First, they detected gravitational redshift. The light from the star was stretched to longer, redder wavelengths as it climbed out of the black hole's deep gravity well. Second, they observed the Schwarzschild precession. The orientation of the star's elliptical orbit shifted slightly with each pass, tracing a rosette pattern over time exactly as predicted by Einstein. The dance of the S-stars is more than just a celestial spectacle. It is a profound confirmation of our understanding of gravity and a direct window into the nature of the enigmatic beast that lurks at the heart of our galaxy. At the very heart of the Milky Way, the gravitational anchor around which 100 billion stars revolve, sits Sagittarius A, pronounced A star. It is our galaxy's supermassive black hole, a monster containing the mass of over 4 million suns crushed into a space smaller than the orbit of Mercury. Yet for a beast of such epic proportions, Sagittarius A is surprisingly tame. Compared to the brilliant, violently active black holes we see at the centers of other galaxies, which blast out powerful jets and outshine all their host galaxies' stars combined, ours is remarkably quiet. Scientists often refer to it as quiescent, or a sleeping giant. It does not have a vast glowing accretion disk of superheated material swirling into a death spiral. It seems to be on a starvation diet, consuming very little of the surrounding gas and dust. But sleeping does not mean dead. Every so often the giant stirs. When a stray gas cloud or the remnants of a disrupted star drift too close, They are ensnared by the black hole's immense gravity. As this material spirals inward, it is compressed and heated to millions of degrees, unleashing a brilliant flare of energy that can be detected by X-ray and infrared telescopes. In 2019, astronomers witnessed the brightest such flare ever recorded from Sagittarius A, when it suddenly lit up in infrared light, growing over 75 times brighter than usual for a few hours, before fading back into obscurity. These sporadic flares are a constant reminder that while the black hole is mostly dormant, it is still a powerful engine capable of consuming matter and releasing bursts of incredible energy. It is a volcano that sleeps for long periods, but occasionally sends up a warning puff of smoke, hinting at the immense power that lies beneath the surface. The relative peace of our galactic center is likely a matter of fuel supply. There simply isn't a large, steady flow of gas reaching the black hole today. Our galaxy is in a quiet phase of its life. But it wasn't always this way, and it won't be in the future. While Sagittarius A is a sleeping giant, its slumber is fitful, punctuated by brief, violent awakenings. Scientists using telescopes like NASA's Chandra X-ray Observatory have detected small flares erupting from the black hole's vicinity almost daily. These are brief flashes lasting from a few minutes to a few hours, signaling that small clumps of matter are constantly being torn apart and consumed. Each flare is a tiny cosmic scream as material crosses the event horizon, the point of no return. But sometimes the black hole produces something far more dramatic. In 2022, after years of painstaking work, the Event Horizon Telescope collaboration released the first ever image of Sagittarius A. It was not a photograph in the traditional sense, but a map constructed from radio waves collected by a global network of telescopes acting as a single Earth-sized observatory. The image revealed a glowing donut-shaped ring of superheated gas and plasma swirling around a dark central region. That dark patch is the shadow of the black hole, the silhouette cast by its immense gravity, a region where light itself is trapped and pulled into the abyss. The bright ring is the material just outside the event horizon heated to billions of degrees and accelerated to near the speed of light by the black hole's powerful magnetic fields. The image confirmed not only the black hole's existence, but also its mass and size, which matched the predictions from the orbits of the S stars perfectly. These flares and the glowing ring of plasma are the modern-day whispers of the giant. But there is compelling evidence that in the distant past, it roared. Evidence for a more violent history comes from structures far outside the galactic center, hinting that our black hole was once a far more active and ferocious beast. High above and far below the dense, glittering plain of the Milky Way, there exist two colossal, ghostly structures, invisible to the naked eye, but glowing fiercely in the most energetic form of light gamma rays. Discovered in 2010 by the Fermi Gamma Ray Space Telescope, these are the Fermi bubbles. Each bubble is a massive symmetrical lobe of high-energy plasma, stretching an astonishing 25,000 light-years from the galactic center, spanning a total distance nearly as large as the radius of the galaxy's visible disk. They are the clear signature of a stupendous and relatively recent outburst of energy from the heart of our galaxy. What could have created such monumental structures? There are two leading theories, both pointing to a period of intense activity in the galactic core millions of years ago. The first hypothesis blames our supermassive black hole, Sagittarius A. Perhaps a few million years in the past, a large gas cloud or a dense star cluster was captured by the black hole. As this material was consumed, it would have formed a temporary brilliant accretion disk, unleashing a torrent of energy. This event could have launched a pair of powerful high-speed jets of particles blasting outward from the black hole's poles. These jets would have plowed through the diffuse gas of the galactic halo, inflating the giant gamma-ray emitting bubbles we see today. We see such jets erupting from the supermassive black holes in many other active galaxies. The Fermi bubbles may be the fading smoke rings of a time when our own galaxy was similarly active. The second possibility points to a massive burst of star formation near the galactic center. If thousands of massive stars formed and subsequently exploded as supernovae in a relatively short period, their combined shockwaves could create a powerful superwind. This wind would be strong enough to blow gas and high-energy cosmic rays out of the galactic disk and into the halo, inflating the bubbles from the bottom up. It's also possible that both events happened in concert with a starburst feeding gas to the black hole, triggering a jet and creating a combined explosive event. Whatever their origin, the Fermi bubbles are a stark reminder that our galaxy is not a static place. It has a dynamic, violent history. They are the ghostly remnants of a past cataclysm, a testament to the immense power that can be unleashed from the galactic heart, and a warning that the sleeping giant at our galaxy's center may not sleep forever. The Fermi bubbles are the most dramatic evidence of a larger ongoing process known as galactic weather. Just as Earth's atmosphere has wind storms and pressure systems, a galaxy has a complex dynamic halo filled with flows of gas-energetic particles and magnetic fields. This weather is driven by the two great engines of a galaxy star formation and the activity of its central supermassive black hole. The combined stellar winds from thousands of hot young stars and the explosive shockwaves from supernovae create powerful galactic winds. These winds can sweep through the disk, pushing gas and dust out into the halo. This process is a form of feedback regulating the galaxy's growth. By blowing away the raw fuel for star formation, these winds can temporarily shut down the birth of new stars in a region, preventing the galaxy from burning out too quickly. At the same time, the supermassive black hole can have an even more profound impact. When Sagittarius A consumes matter, it doesn't just swallow it quietly. The process can release enormous amounts of energy-launching jets, or wide-angle outflows of hot plasma that travel at near the speed of light. These outflows punch through the interstellar medium and inflate vast cavities in the galactic halo like the Fermi bubbles. This black hole feedback is one of the most important processes in shaping the evolution of massive galaxies. It can heat the gas in the halo to millions of degrees, preventing it from cooling and falling back onto the disk to form new stars. In this way, the black hole acts like a galactic thermostat, regulating the star formation rate of the entire galaxy and influencing its size, shape, and color over billions of years. This constant circulation of matter and energy gas flowing into the disk, being forged into stars, then being blown back out into the halo by winds and jets, only to eventually cool and rain back down again, is the galaxy's metabolism. The Fermi bubbles and other fainter structures seen in X-rays and radio waves are the visible signs of this grand cosmic cycle, the weather patterns of our vast galactic ecosystem. Woven throughout the Milky Way, guiding the flow of gas and steering the paths of cosmic rays, is an immense and complex structure we can never see directly: the galactic magnetic field. It is an invisible skeleton of force, a tangled web of magnetic lines that permeates the disk, the bulge, and the halo. Though vastly weaker than the magnetic field of a household magnet, its influence over cosmic scales is profound. These magnetic fields are generated by the motion of charged particles in the galaxy's plasma, a process known as a galactic dynamo. The rotation of the galaxy twists and stretches these field lines, amplifying and organizing them into large-scale patterns. Astronomers map this invisible structure using clever indirect methods. One way is by observing polarized light. As starlight travels through space, it can be polarized by interstellar dust grains that have been aligned by the magnetic field. By measuring the direction of this polarization, scientists can trace the orientation of the magnetic field lines. Another technique uses the Faraday effect. When polarized radio waves from distant sources like pulsars or quasars pass through the magnetized plasma of our galaxy, their plane of polarization is rotated. The amount of rotation reveals the strength and direction of the magnetic field along the line of sight. These methods have revealed a magnetic field that is both ordered and chaotic. In the galactic disk, the field lines seem to largely follow the spiral arms wrapping around the galaxy in a coherent, large-scale spiral. But this orderly pattern is filled with turbulence. Supernova explosions and stellar winds create tangled, chaotic magnetic bubbles that disrupt the larger field. High above and below the disk in the halo, the magnetic field takes on a different shape, forming vast arching loops that may connect the galaxy's poles, possibly shaped by the outflows that created the Fermi bubbles. Near the galactic center, the field becomes even more intense and complex. Radio observations have revealed strange, highly ordered thread-like structures called non-thermal radiofilaments. These are long, thin streams of plasma, some stretching for hundreds of light-years, glowing brightly in radio waves. They are thought to be streams of high-energy electrons, spiraling along incredibly strong magnetic field lines, though their exact origin remains a mystery. This magnetic skeleton plays a critical role in the galaxy's life. It can support gas clouds against gravitational collapse, thereby regulating the rate of star formation. It acts as a cosmic shield, deflecting some of the charged particles from interstellar space. And it serves as the invisible highway system that traps and guides the galaxy's most energetic particles. The space between the stars is not empty. It is filled with a constant shower of high-energy particles known as cosmic rays. These are atomic nuclei, mostly protons, but also heavier elements that have been accelerated to nearly the speed of light. They are born in the universe's most violent events, the shockwaves of exploding supernovae, the swirling chaos around black holes, and the turbulent environments of young, massive stars. A single cosmic ray particle can carry more energy than a tennis ball served by a professional player, all packed into a subatomic projectile. On Earth, we are largely protected from this relentless bombardment by our planet's atmosphere and magnetic field. But in the wider galaxy, these particles are a powerful force. They travel across vast distances, and their paths are dictated by the galaxy's magnetic skeleton. Because cosmic rays are charged particles, they cannot travel in straight lines through the magnetized interstellar medium. Instead, they are forced to spiral along the magnetic field lines, bouncing and scattering as the field twists and turns. The galactic magnetic field acts like a vast, invisible pinball machine, trapping these particles within the galaxy for millions of years before they can escape into intergalactic space. This confinement is crucial. It means that the cosmic rays produced by supernovae and other events build up over time, creating a pervasive high-energy background radiation that fills the entire galactic volume. This cosmic ray, C, has enough pressure to influence the structure of the galaxy, helping to support the galactic disk against gravitational collapse. Cosmic rays also play a key role in the chemistry of the cosmos. As they zip through interstellar clouds, they can collide with atoms and molecules, breaking them apart or ionizing them. This process can trigger the formation of new, more complex molecules, the very building blocks from which planets and life are made. The magnetic field lines therefore act as cosmic ray highways, channeling these energetic particles and their creative and destructive potential throughout the galaxy. The beautiful glowing filaments of a nebula and the invisible powerful currents of cosmic rays are two sides of the same cosmic story, both shaped and guided by the unseen hand of the galactic magnetic field. Far beyond the bright, bustling disk of the Milky Way, in the vast, dark expanse that surrounds our galaxy, lies a ghostly realm known as the stellar halo. This is a sparse, spherical region, mostly empty, containing only about 1% of the galaxy's stars. There are no brilliant nebulae here, no dense lanes of gas to fuel new star birth. Instead, the halo is home to the galaxy's oldest and most enigmatic inhabitants. The stars of the halo drift slowly through space, scattered like ancient dust around a glowing core. Most of them are very old, much older than our Sun, with some dating back to the very dawn of the universe, nearly 13.6 billion years ago. These primordial stars are the survivors of the first generations of star formation. They are metal poor, meaning they contain very few elements heavier than hydrogen and helium. They were born from the pristine gas of the early cosmos before countless supernova explosions had enriched the universe with the carbon, oxygen, and iron that are common in younger stars like our Sun. These stars do not orbit the galaxy in the orderly circular paths of their disk-bound cousins. Instead, they follow long, looping, highly elliptical trajectories, moving in all directions. Some even orbit backward relative to the galaxy's spin. This chaotic motion is a clear sign that these stars did not form within the Milky Way's disk. They are immigrants, stellar refugees from a bygone era. In a very real sense, the halo is a cosmic graveyard, a vast cemetery filled with the remains of smaller galaxies that the Milky Way has consumed over its long and violent history. Large galaxies like the Milky Way did not spring into existence fully formed. They grew over billions of years through a relentless process of cosmic acquisition, galactic cannibalism. Our galaxy is a predator that has become large and massive by consuming its smaller neighbors. When a smaller dwarf galaxy strays too close to the Milky Way, it is ensnared by our galaxy's immense gravitational pull. The encounter is not a sudden collision, but a slow, agonizing process of tidal disruption. The side of the dwarf galaxy closer to the Milky Way feels a stronger gravitational tug than the far side. This differential pull stretches the smaller galaxy, pulling it apart, like cosmic taffy. Its outermost stars are stripped away, first peeling off into long, faint trails of light that follow the dwarf's orbital path. These are called stellar streams, or tidal tails. Over the course of several orbits, which can take billions of years, the dwarf galaxy is slowly unraveled. Its stars are dispersed into the vastness of the Milky Way's halo, while its core may survive for a time before it, too, is eventually dissolved. The halo is filled with the ghosts of these consumed galaxies. The stars from each disrupted dwarf galaxy still travel together in a coherent stream, a faint memory of the structure they once belonged to. They are the archaeological evidence of the Milky Way's violent growth fossils that allow astronomers to reconstruct our galaxy's merger history. By studying the positions, motions, and chemical compositions of these stellar streams, scientists can identify the remnants of dozens of past mergers. They can piece together when these galaxies were captured, what their orbits were like, and how they contributed to the buildup of the Milky Way's mass and structure. The process of galactic cannibalism is not over. The Milky Way is still consuming its neighbors today. The Sagittarius dwarf galaxy is currently being torn apart, its stars forming a massive stream that wraps around our entire galaxy. The large and small Magellanic Clouds, our largest satellite galaxies, are on a path that will likely lead to their eventual absorption over the next few billion years. Our galaxy is a living, growing entity, its serene beauty belying a history and a future of cosmic violence and consumption. One of the most spectacular pieces of evidence for ongoing galactic cannibalism is the Sagittarius stream. Discovered in the 1990s, this is a vast looping ribbon of stars that wraps around the entire Milky Way, a ghostly structure born from the slow destruction of the Sagittarius dwarf spheroidal galaxy. This small satellite galaxy is currently on a polar orbit around the Milky Way, meaning it passes over and under our galaxy's disk. With each pass, the powerful tidal forces of the Milky Way strip more stars' gas and dark matter from the smaller galaxy. These stolen stars are drawn out into two long tidal tails, one trailing behind the dwarf galaxy and one leading ahead of it. Over billions of years, these tails have stretched and spread until they now form a continuous stream that encircles our galactic home. The Sagittarius stream is a fossil in motion, a direct visible record of a merger in progress. By mapping the stream's path and studying the properties of its stars, astronomers can run the clock backward and model the history of the collision with incredible detail. They can determine that the Sagittarius dwarf has likely made several passes through the Milky Way's disk over the last few billion years. The discovery of the stream also solved a long-standing puzzle about certain globular clusters. A handful of these ancient star clusters, like Messier 54, seem to have strange properties and orbits that didn't fit with the rest of the Milky Way's population. It is now clear that these clusters were not born in our galaxy. They were the original globular clusters of the Sagittarius dwarf, stolen along with its stars, and now orbiting within the stream. The repeated passages of the Sagittarius dwarf have also had a profound effect on the Milky Way itself. The gravitational ripples from these collisions are thought to be responsible for some of the warps and oscillations we see in our galaxy's disk. The Sagittarius stream is not just a relic of destruction. It is a testament to the powerful creative forces of gravity that continue to shape and reshape our galaxy today. Visible to the naked eye as two faint cloud-like smudges in the southern night sky are the Milky Way's largest and most famous satellite galaxies, the large and small Magellanic Clouds. For millennia, they were thought to be serene companions, locked in a stable, eternal orbit around our galaxy. But recent observations have revealed a far more dramatic and dynamic story. These two dwarf galaxies are relative newcomers to our neighborhood, likely on their very first pass by the Milky Way after a long journey across intergalactic space. The Large Magellanic Cloud, LMC, about 160,000 light-years away, is a sprawling, irregular galaxy ablaze with furious star formation, most famously in the immense Tarantula Nebula. The Small Magellanic Cloud, SMC, slightly farther at 200,000 light-years, is smaller and more chaotic. The two are gravitationally bound to each other, a binary system currently being ensnared by the Milky Way's gravity. Their presence is wreaking havoc on our galaxy's outer regions. Their combined gravitational pull is likely the primary cause of the large-scale warp in the Milky Way's disk. As the LMC, which is far more massive than previously thought, plunges through our galaxy's dark matter halo, it creates a gravitational wake, like a ship plowing through water. This wake displaces the dark matter and slightly shifts the position of our galactic disk, causing it to wobble. At the same time, the Milky Way's gravity is exacting a heavy toll on the clouds. A vast, invisible trail of hydrogen gas, known as the Magellanic Stream, is being torn from the two galaxies, stretching across more than 100 degrees of the sky. This stream is a testament to the tidal forces at play, slowly stripping the clouds of the raw material they need for future star formation. This gas may eventually rain down upon the Milky Way, providing a fresh supply of fuel to ignite new stars in our own galaxy. We are witnessing the beginning of a grand merger. Over the next 2.5 billion years, the Magellanic Clouds will likely be completely consumed their stars, and gas scattered and absorbed into the Milky Way's halo and disk, another pair of cosmic ghosts in our galaxy's ever-growing graveyard. Our leading theory of cosmology, the Lambda Cold Dark Matter LCDM model, has been incredibly successful at explaining the large-scale structure of the universe. When run on supercomputers, simulations based on this model show a universe where dark matter clumps together under gravity, forming halos that then attract ordinary matter to create galaxies. These simulations accurately predict the cosmic web of galaxy clusters and filaments we observe. However, on smaller scales, a significant puzzle emerges: the missing satellites problem. The simulations predict that a large dark matter halo, like the one surrounding the Milky Way, should contain thousands of smaller subhalos. These should be the gravitational seeds for thousands of dwarf satellite galaxies. Yet when we look at the sky, we see only a few dozen. Where are the rest? This glaring discrepancy has been one of the biggest challenges to the standard model of cosmology for years. One possible solution is that most of these dark matter subhalos are simply dark. Perhaps in the smallest subhalos, the gravitational pull was never strong enough to capture enough gas to ignite star formation, or perhaps the radiation from the first stars in the universe blew away the gas before it had a chance to form stars. If this is the case, the Milky Way could be surrounded by thousands of dark galaxies, invisible clumps of dark matter with no stars to reveal their presence. Another idea is that our telescopes simply haven't been powerful enough to see the faintest galaxies. In recent years, deep sky surveys like the Dark Energy Survey have indeed discovered a new class of ultra-faint dwarf galaxies, some containing only a few hundred stars. Each new discovery helps to close the gap between theory and observation, but a significant discrepancy remains. The missing satellites problem forces us to question our fundamental understanding of either dark matter or galaxy formation. Perhaps dark matter is more complex than we thought, with properties that suppress the formation of small structures. Or perhaps the physics of star formation and feedback from supernovae in the early universe are more efficient at quenching galaxy growth than our models currently account for. The search for these missing satellites is a hunt for the very soul of our cosmological model. A test that will either vindicate our understanding or force us toward a new, more complete theory of the cosmos. Drifting through our galaxy's halo is a star that for a time seemed to break the universe. Officially catalogued as HD 140283, it is more evocatively known as the Methuselah star. It is one of the oldest stars ever discovered, and its existence poses a fascinating challenge to our cosmic timeline. The Methuselah star is extremely metal-poor, a clear sign that it formed in the very early universe, before many generations of supernovae had enriched the cosmos with heavier elements. When astronomers first tried to calculate its age by analyzing its brightness distance and composition, they arrived at a shocking number: 14.5 billion years, with an uncertainty of about 800 million years. This created a profound paradox. Our best measurements of the universe's age, based on the expansion rate of the cosmos and the cosmic microwave background radiation, place it at a firm 13.8 billion years. How could a star be older than the universe itself? The answer, of course, is that it can't. The paradox highlighted the incredible difficulty and uncertainty involved in measuring the ages of the most ancient stars. The calculation depends on precise models of stellar evolution and exquisitely accurate measurements of the star's properties, particularly its distance. A small error in any of these inputs can lead to a significant change in the calculated age. Subsequent observations, especially a more precise distance measurement from the Hubble Space Telescope, allowed astronomers to refine their calculations. They also improved the theoretical models accounting for factors like how elements diffuse within a star over time. With these updates, the age of the Methuselah star was revised downward to a more comfortable 13.00 to 13.2 billion years. While this resolves the paradox, the star remains a remarkable object. It must have formed just a few 100 million years after the Big Bang, making it a true relic of the cosmic dawn. Like many halo stars, its wild looping orbit suggests it wasn't born in the Milky Way, but was likely a member of a small dwarf galaxy that was long ago consumed. The Methuselah star is a cosmic time capsule, a direct link to the universe's infancy, reminding us that the history of the cosmos is written in the light of its oldest survivors. For much of human history, the search for life beyond Earth focused on stars like our Sun. But in recent years, our attention has shifted to a far more common, yet much fainter class of stars, red dwarfs. These small, cool stars make up roughly 75% of the stellar population of the Milky Way. And one of them, a faint star named TRAPPIST-1, has become a beacon of hope in the search for habitable worlds. Located just 40 light-years away, TRAPPIST-1 is an ultra-cool dwarf star, not much larger than the planet Jupiter. In 2017, astronomers announced the stunning discovery that this tiny star hosts a compact system of 7 rocky Earth-sized planets. What makes this system so extraordinary is that at least 3 and possibly more of these planets orbit within the star's habitable zone, the region where temperatures could be just right for liquid water to exist on a planet's surface. Because red dwarfs are so much cooler than the Sun, their habitable zones are much closer in. The entire TRAPPIST-1 system would fit comfortably inside the orbit of Mercury. This proximity makes the planets easier to study. As they pass in front of their star, a technique called transit photometry telescopes, like the James Webb Space Telescope, can analyze the starlight filtering through their atmospheres, searching for the chemical fingerprints of water methane and other potential biosignatures. However, life around a red dwarf would face unique challenges. Planets in such close orbits are likely tidally locked, with one side perpetually facing the star in constant daylight and the other frozen in eternal night. This could create extreme temperature differences, though a thick atmosphere might be able to circulate heat and create a more temperate climate. A bigger danger comes from the star itself. Young red dwarfs are notoriously volatile, frequently unleashing powerful stellar flares that could strip away a planet's atmosphere and bathe its surface in lethal radiation. The question of whether the TRAPPIST-1 planets and worlds like them throughout the galaxy could overcome these challenges and harbor life is one of the most exciting frontiers in modern astronomy. If life can thrive in such different conditions, then the number of potentially habitable worlds in our galaxy could be in the hundreds of billions, making it seem almost inevitable that we are not alone. In 2013, the European Space Agency launched a spacecraft that would revolutionize our understanding of the Milky Way. Its name was Gaia, and its mission was to create the most precise three-dimensional map of our galaxy ever attempted. By repeatedly measuring the positions, motions, and brightness of over 1 billion stars, Gaia has provided an unprecedented dataset for the field of galactic archaeology. Gaia's power lies in its ability to measure not just where stars are, but how they are moving in 3 dimensions, their proper motion across the sky, and their radial velocity toward or away from us. This allows astronomers to trace the orbits of stars through the galaxy and identify groups of stars that are moving together, even if they are now scattered across the sky. With this data, astronomers can act like cosmic detectives, uncovering the remnants of ancient galaxies that merged with the Milky Way billions of years ago. When a dwarf galaxy is consumed, its stars are stripped away into long tidal streams. While these streams become faint and diffuse over time, the stars within them retain a common kinematic fingerprint. They move with similar velocities and in similar directions. Gaia's data allows scientists to pick out these coherent groups from the background of Milky Way stars, revealing the ghostly skeletons of long-dead galaxies. This technique has allowed astronomers to identify numerous new stellar streams in the halo, each one corresponding to a different merger event. They can reconstruct the orbits of these ancient galaxies, estimate their mass, and determine when they were absorbed. Gaia has transformed our view of the galactic halo from a sparse, random collection of old stars into a complex, structured graveyard filled with the clear evidence of our galaxy's violent, cannibalistic past. One of the most profound discoveries to come from the Gaia mission was the identification of a massive ancient merger event that fundamentally shaped the early Milky Way. By analyzing the motions of stars in the galactic halo, astronomers found a huge population of stars moving on strange, elongated, and retrograde backward orbits. These stars were not a small stream. They made up a significant fraction of the inner halo. Their chemical composition was also distinct from typical Milky Way stars. This vast collection of stellar ghosts was the clear remnant of a major collision with a single, relatively large dwarf galaxy. This ancient galaxy, now named Gaia Enceladus, or the Gaia sausage, due to its elongated shape in velocity plots, is believed to have collided with a still young Milky Way around 10 billion years ago. The collision was a cataclysmic event. The Gaia Enceladus galaxy was completely shredded, its stars scattered throughout the halo. The impact was so violent that it puffed up the early Milky Way disk, helping to form the thick disk, a population of older stars that exists in a thicker layer than the main thin disk where our Sun resides. Many of the globular clusters in our halo are also thought to have been brought in with this merger. The discovery of Gaia Enceladus was a landmark moment in galactic archaeology. It confirmed that our galaxy's history was not one of just gentle, slow growth, but was punctuated by massive transformative events. It provided a clear picture of how the stellar halo and thick disk were built. Thanks to Gaia, we can now see the faint, lingering ghost of a long-dead galaxy, its presence still felt in the motions of billions of stars, a testament to one of the most important events in the life of the Milky Way. The question of whether we are alone in the universe leads to a grander concept. Are certain regions of a galaxy more conducive to the emergence and survival of complex life than others? This idea is known as the Galactic Habitable Zone. GHZ, a cosmic-scale version of the habitable zone around a star. It suggests that a planet's location within the galaxy could be just as important as its distance from its sun. The theory proposes a sweet spot, a ring-shaped region within the galactic disk where conditions are just right. If a planet is too close to the galactic center, the environment is dangerously chaotic. The density of stars is much higher, increasing the risk of a nearby supernova explosion, which could sterilize a planet with a blast of deadly radiation. The intense gravity in the core can also disrupt planetary orbits, flinging worlds into their stars or out into interstellar space. Furthermore, the radiation from the central supermassive black hole can be intense. Conversely, if a planet is too far out in the galaxy's remote suburbs, it faces a different problem, a lack of building materials. The heavy elements or metals that are necessary for forming rocky planets and are the basis of life as we know it, carbon, oxygen, iron, are forged in stars and scattered by supernova. The density of these elements is highest near the galactic center and decreases with distance. In the outer reaches of the galaxy, there may not be enough metallicity to form Earth-like planets in the first place. The Galactic Habitable Zone is the proposed compromise between these two extremes. It is a region far enough from the core to be safe from its worst dangers, but close enough to have a sufficient concentration of heavy elements to build habitable worlds. Our solar system, located about 26,000 light-years from the center, sits comfortably within most theoretical models of this zone. This has led some to speculate that our location is not a coincidence, but a key reason why complex life was able to flourish on Earth over billions of years. The concept is still debated, but it provides a powerful framework for thinking about where we might best direct our search for extraterrestrial intelligence. The Milky Way, for all its vastness, is not a lonely island in the cosmic ocean. It is a leading member of a gravitationally bound family of galaxies known as the Local Group. This group is a diverse collection of over 80 known galaxies spread across a region of space some 10 million light-years in diameter. At the heart of the Local Group are its two titans, the Milky Way and the Andromeda galaxy M31. These two massive spiral galaxies dominate the group, each with its own retinue of smaller satellite galaxies orbiting it. Andromeda is the true monarch of the group, slightly larger and more massive than our own galaxy. The third largest member is the Triangulum galaxy M33, a smaller spiral that may itself be a satellite of Andromeda. The rest of the Local Group's population consists of a swarm of dwarf galaxies of various shapes and sizes, from irregulars like the Magellanic Clouds to faint spheroidal systems containing only a few thousand stars. These galaxies are not flying apart with the overall expansion of the universe. Instead, they are bound together by their mutual gravity, orbiting a common center of mass located somewhere between the Milky Way and Andromeda. Their motions tell a story of constant interaction, tidal stripping, and future mergers. The Local Group provides a unique cosmic laboratory. It allows us to study galaxy formation, dark matter, and stellar evolution in our own backyard. We can resolve individual stars in these nearby galaxies, study their histories, and watch the process of galactic cannibalism unfold in real time. Our place within this group is not static. It is defined by a dynamic gravitational dance that has been playing out for billions of years and will culminate in a spectacular future event. When we look toward the constellation Andromeda, we are looking at our cosmic destiny. The Andromeda Galaxy, our massive spiral neighbor, is hurtling toward the Milky Way at a speed of approximately 110 kilometers per second. This is not a near miss. We are on a direct collision course. For billions of years, the mutual gravity between these two galactic titans has been pulling them inexorably together. In about 4.5 billion years, this slow-motion cosmic approach will culminate in the beginning of a galactic merger of epic proportions. This will not be a collision in the conventional sense. Galaxies are mostly empty space, and the odds of any two individual stars actually hitting each other are infinitesimally small. Rather, it will be a collision of gravity. As the two galaxies begin to pass through each other, their immense gravitational fields will intertwine, warping and distorting their elegant spiral structures. Powerful tidal forces will stretch the galaxies, flinging long streams of stars and gas out into intergalactic space. The vast clouds of interstellar gas within each galaxy will slam into each other, triggering a spectacular and galaxy-wide burst of star formation, a starburst that will light up the merging system. After the first pass, which will take hundreds of millions of years, the two galaxies will separate, their structures mangled and chaotic. But their gravitational bond will be unbreakable. They will slow down, turn around, and fall back together for a second, even more disruptive encounter. This cosmic dance of repeated passes and mergers will continue for over 1 billion years, until finally the two galaxies settle and merge into one. What will be the ultimate result of this grand cosmic collision? Using powerful supercomputers, astronomers can simulate this future event with stunning detail. They input the known properties of the Milky Way and Andromeda, their mass, size, velocity, and dark matter content, and let the laws of gravity play out over billions of years. The simulations consistently show the same outcome. The two beautiful spiral galaxies will be destroyed, their iconic arms torn apart, and their stars scattered. The chaotic merger will result in the formation of a single, much larger galaxy. This new entity has been nicknamed Milkomeda. Milkomeda will not be a spiral galaxy. The merger process randomizes the orbits of the stars, transforming the ordered rotating disks into a vast, roundish, three-dimensional cloud of stars. It will be a giant elliptical galaxy, one of the most common types of galaxies in the universe, often found at the centers of galaxy clusters. During the merger, the two supermassive black holes from the hearts of the Milky Way and Andromeda will eventually spiral toward each other and merge as well, forming an even more massive black hole at the center of Milkomeda. The intense starburst triggered by the colliding gas clouds will use up most of the available fuel, leaving the new galaxy with very little gas for future star formation. Milkomeda will be an old, red and dead galaxy, filled primarily with aging reddish stars and lacking the vibrant blue nebulae of its spiral predecessors. Our night sky will be forever changed. During the merger, the sky would be filled with brilliant new star clusters and the distorted, overlapping shapes of the two galaxies. After the merger settles from our Sun's new position within Milkomeda, the sky would be dominated by the bright, dense glow of the new elliptical core. The familiar faint band of the Milky Way would be gone, replaced by a more uniform, star-filled haze. While the merger of the Milky Way and Andromeda will be a cataclysmic event on a galactic scale, the fate of our own solar system is likely to be far less dramatic. Given the vast distances between stars, the chance of our Sun colliding with another star is practically zero. Our solar system will almost certainly survive the merger intact. However, our position within the new galaxy will change dramatically. Simulations show that there is a high probability that the solar system will be thrown much farther out from the galactic core than it is today. As the merger randomizes stellar orbits, we could be gravitationally flung into the sparse outer halo of the new Milkomeda galaxy. Our galactic neighborhood would be completely transformed. The familiar constellations would vanish, replaced by an alien starscape. From this new, distant vantage point, the night sky would be dominated by the bright, featureless glow of Milkomeda's core. But there is a more pressing and certain fate for our world that will unfold on a similar timescale. In about 4 to 5 billion years, just as the galactic merger begins, our own Sun will be nearing the end of its life. It will exhaust the hydrogen fuel in its core and begin to swell into a red giant. Its expanding outer layers will engulf Mercury and Venus and possibly Earth itself. Even if Earth survives being swallowed, the intense heat will boil away its oceans and strip its atmosphere, rendering our planet a scorched, lifeless rock. After this phase, the Sun will shed its outer layers to form a beautiful planetary nebula, leaving behind a dense, hot core, a white dwarf. The surviving planets of our solar system will continue to orbit this faint, cooling stellar remnant in a cold and dark system. Therefore, long before the chaos of the galactic merger fully subsides, the story of life on Earth will have already come to an end, not through a galactic cataclysm, but through the natural life cycle of our own star. The future inhabitants of our solar system, if any exist, will witness the birth of a new galaxy from the silent, frozen surface of a world orbiting a dying sun. The Milky Way is vast and ancient home to hundreds of billions of stars and likely trillions of planets. Given these staggering numbers, it seems statistically probable that life and even intelligent civilizations should have arisen many times over. This leads to the profound and unsettling question first posed by physicist Enrico Fermi. If the galaxy should be teeming with life, where is everybody? This is the Fermi paradox. The great silence from the stars is one of the deepest mysteries we face. Are we truly alone? Or is there another explanation for the silence? Perhaps civilizations are too far apart in space and time. Perhaps they inevitably destroy themselves before they can achieve interstellar travel. Perhaps they exist, but are hiding from us, observing us from afar. Or perhaps life is simply far, far rarer than we imagine. As we peer into the deep future, this silence becomes even more profound. In 100 billion years, the universe will be a vastly different place. The merger with Andromeda will be a distant memory. Milky will be an old, quiet galaxy of faint red stars. But the most significant change will be driven by the accelerating expansion of the universe. Fueled by dark energy, the fabric of space is stretching at an ever-increasing rate. This means that all the other galaxies and galaxy clusters beyond our local group are receding from us, and their speed is increasing. Eventually, they will be moving away from us faster than the speed of light. Their light will no longer be able to reach us. They will cross our cosmic horizon and vanish from our view forever. The night sky of Milky will be dark and achingly lonely. All other galaxies will have disappeared, leaving our own as the only visible island of light in an endless, empty void. Any civilization born in that far future would have no evidence of the Big Bang, the cosmic web, or the existence of other galaxies. They would look up at the sky and conclude that their galaxy was the entire universe. The story of the cosmos, from its fiery birth to its grand structure, would be lost to them. The ultimate fate of the matter within our galaxy is even stranger. Over trillions upon trillions of years, stars will burn out, leaving behind a graveyard of black dwarfs, neutron stars, and black holes. Even protons may eventually decay, causing all ordinary matter to slowly dissolve into a faint bath of radiation. Finally, over truly unimaginable timescales, even the supermassive black holes will evaporate through Hawking radiation until nothing is left but a cold, dark, and empty universe. The epic story of the Milky Way, from its first stars to its final merger, is a journey of creation, destruction, and constant change. We are fortunate to live in a time when we can still see the evidence of this grand cosmic narrative, a brief, privileged moment before the lights of the universe begin to fade one by one into an eternal silence. What do you think? Send us your thoughts in the comments. And if you enjoyed this journey, consider leaving a like and subscribing. Thanks for watching. The epic story of the Milky Way, from its first starlit myths to its silent, distant future, is ultimately our own story. We are the brief, wondrous consciousness of the cosmos, a fleeting moment in which the universe can know itself. What does this journey through deep time inspire in you? We would love to read your thoughts in the comments below. If this voyage has expanded your perspective, don't forget to subscribe to Astro Horizons and hit the notification bell so you never miss an expedition into the unknown. Thank you for watching Astro Horizons.